Okay, so let's solve for this problem here that it was assigned to you on September 4th. We have here the motion of a car in a straight track, and this is the velocity as a function of time of that car's motion. So we're going to answer a series of questions. Okay, the first question, question A, is what happens to the car? Describe what happens to the car at time is equal to 1 second. Okay, so let's look at our graph. We're concerned with the motion of the car at 1 second. So at this point, notice how it goes. Your line actually breaks at this point. Okay, it was going up and then now it's going down. So let's examine what's happening to the graph at time is equal to 0. At time is equal to 0, the graph has a velocity of 0 meters per second. Okay, now at 1 second, the graph has a velocity, or the car, has a velocity of 20 meters per second. So that means that within the first second, the change in velocity, okay, for the first 1 second was equal to 20 minus 0, which is 20 meters per second. And the change in velocity was positive, okay, so that change was positive. Now, if you look at the line here, okay, the slope of this line gives you the acceleration. And this slope is positive. Therefore, we know that our acceleration is positive. So acceleration is positive. We know velocity is positive because all the velocity here is above the x-axis, or the time axis in this case. And so because acceleration is positive and velocity is positive, they both have the same sign, we know that our object is increasing speed. Okay, so we have increasing speed or increasing velocity. Now, at time is equal to 1 second, okay, the line becomes negatively sloped, okay? So that means the following, okay? So we're gonna look at this part right here. Notice how the velocity is still positive, okay? We are still above the t-axis. So velocity is positive here, okay? Velocity is positive. Acceleration in this case is now negative. And because these two signs are different, now we have decreasing speed. So to answer our part A, what happens to the object at time is equal to 1 second, we say that the object starts decreasing speed. So at time is equal to 1 second, the object decreases velocity. And that would be your answer for part A. Okay, now let's move on to part B. Part B says, how does the car's average velocity between t is equal to 0 and t is equal to 1 second, okay, so average velocity between 0 and 1 second, and how does that compare to its average velocity between 1 and 5 seconds? So we're going to compare this one to the average velocity between 1 and 5 seconds. Now, because this is constant acceleration, we have a straight sloped line right here. We can find our average velocity by using the formula for average, which is you add up your 2 points that you have and you divide by the number of points, which is 2 in this case. We do the same thing for the average velocity between 1 and 5. Okay, so it's going to be initial velocity plus final velocity divided by 2. Now, between 0 and 1 second, our initial velocity is 0. Okay, so this is going to be 0 plus, and then final velocity is 20 meters per second at that point, and then we divide by 2. 0 plus 20 is 20, divided by 2 is 10, so we have an average velocity of 10 meters per second, and that's going to be positive. Now, Let's do the same thing for 1 to 5 seconds. So for 1 to 5 seconds, we have that our initial velocity is going to be at 1 is 20 meters per second. Our final velocity at 5 seconds is 0 meters per second. And then we divide that by 2. 20 plus 0 divided by 2 is going to give you 10 meters per second as well, which means that the average velocity between 0 and 1 second will be the same as the average velocity between 1 and 5 seconds, okay? So they are equal. Let's move on to question number, letter C, okay? What is the displacement of the car from time equals to time t equals to 0 and t is equal to 7 seconds? So we're trying to find the displacement of the car from 0 to 7 seconds. And the way we do this is by finding the area under the curve. So we are going to find first the area under this big triangle here. Okay, so we're gonna shade in this area right here. And this here is a triangle. So to find the displacement between 0 and 5 seconds, we're gonna use our formula 1/2 base times height. Okay, so remember the displacement in a velocity time graph is given by the area under the curve. So we have 1/2, our base is 5 seconds, and our height is going to be 20 meters per second. So this right here gives you 1/2 times 5 times 20 will give you 50 meters. Notice how the seconds here cancels the seconds on the bottom of the meters per second, so we're left with meters. So that is a displacement for the first 5 seconds. Now let's find the displacement for between 5 and 7 seconds. Now notice how here the graph is on the bottom, so we're going to find this negative area here, okay? So we're gonna find this area here. Now, so it is the area it makes with the graph and the time axis. So to find that displacement, we're going to say displacement from 5 to 7 seconds. And this is also a triangle, so it'll be 1/2 base times height. So we have 1/2. Our base, it goes from 5 to 7, so our base is 2 seconds. And our height, it goes from 0 to -10. Our height is -10 meters per second. Okay, so this right here gives you 1 times -10 gives you -10 meters. Okay, now to find the total displacement between 0 and 7 seconds, you're going to add up your values. So it's going to be 50 meters plus -10 meters, which gives you 40 meters. And that would be your total displacement from 0 to 7 seconds. Now, let's move on to the next part. Okay, so that's part C. Now, for part D, okay, the question is asking us to plot the car's acceleration during the interval as a function of time. Okay, so let's look at our graph. To find acceleration from a velocity time graph, we need to look at the slope of the line. So remember, acceleration equals the slope in a VT graph. Okay, so we're going to find the acceleration for the first second. Okay, so let's find the acceleration for 0 to 1 second. And the slope of this line is going to be, remember, slope is rise over run. So our rise is 20 meters per second divided by our run, which is 1 second. Okay, so remember that's your change in your change in velocity divided by your time, your change in time. So 20 divided by 1 is going to be 20 meters per second, and that one is positive. Now, let's find our acceleration between 1 and 5 seconds. Okay, so the rise from 1 to 5 seconds is, we can say that it drops 20 meters per second. So it's actually a fall instead of a rise. So it's negative 20 meters per second. And it all happens in a time or a run of 4 seconds. If you notice, it goes from 1 to 5. So your run is 1, 2, 3, 4. So that's 4 seconds. This gives you an acceleration of negative 20 divided by 4 is negative 5 meters per second squared. Now, we need to do the last part, and actually here, this has the same slope as this, so we know that from 5 to 7 seconds, our acceleration will also be negative 5 meters per second. And if you just want to find the slope of this line, just to make sure, it's going to be, it has a fall of negative 10 meters per second, and that happens in a time of 2 seconds, so that would be negative 5 meters per second squared. Okay, this last calculation is unnecessary because you can see that the slope of that line is going to be the same throughout. Okay, now once we have this, it says to plot, so we need to make sure that we have our graph. So we're going to have our graph here. We're going to have our 7 seconds. So it's going to be 1, 2, 3, 4, 5, 6, and 7. And then notice how our acceleration is a constant positive 20 meters per second. So I'm going to say this is 5, 10, 15, and 20. And then I'm going to go negative 5, negative 10, and I don't think I need to go any further. So this is time in seconds. This is going to be acceleration in meters per second squared. Now it's very important that you label your axis and that you label your points as well. Now for the first 1 second, okay, so from here to here, our acceleration was a constant 20 meters per second. So you're going to have a line that looks like this. Okay. Now, once we have that, we need to do the acceleration between 1 and 7 seconds, which is negative 5. So we're going to go here and go all the way to 7. Okay, so this would be, and I made my numbers too close to the line, but that would be your acceleration time graph. So remember, anytime you have a straight sloped line in a velocity time graph, that just tells you that your acceleration is constant as long as that line continues. So right here between 0 and 1 seconds, it's 20 meters per second. And then for the rest of the motion, it's going to be at negative 5 meters per second squared. Okay, and that's how you graph part D. Okay, so we're on to our last one. So I'm going to kind of fold my paper over so you can see a little bit better. Okay, so we have part E that says to make a sketch of the object's position during the interval as a function of time. Assume that the car begins at position x is equal to 0. So we're plotting position versus time. Okay, so let's do our graph here. Now, to find position versus time, remember that what we need to do is we need to find the area under the curve, which we actually already did. Okay, now we're still going to have our 7 seconds. Okay, 1, 2, 3, 4, 6, and 7, and this is time in seconds. And now this is going to be a position versus time. So this is going to be your x in meters. Okay, that's going to be your position. Now, for the first 1 second, okay, notice how your acceleration is positive. We said over here that our acceleration was positive, our velocity was positive, so the object is increasing speed. The way you show increasing speed is by showing a positive slope. So what is going to happen between 0 and 1 second is that your slope is actually going to be curved up with a positive slope. Okay, so we're going to do just kind of like this. Okay, so it's going to look something like this. Okay, notice here that if you were to get any point here and find the tangent line to that point, that would be your instantaneous acceleration at that point. Okay, that would be your acceleration. I'm sorry, your instantaneous velocity, not acceleration. Okay, so we have this right here. Now between 1 and 5 seconds, what happens now is that now you have a negative acceleration and a positive velocity. So now you're decreasing speed. So now you cannot continue going like this upwards on that curve because your speed is actually decreasing all the way to 0 here. So what's going to happen is that you are going to have something that looks something like this. Okay, notice how the slope of this curve actually decreases until at this point it's horizontal, so it is going to be a speed of 0 or a velocity of 0. Okay, now let's look at what happens here. Here we have a negative acceleration because now the graph is below the time axis. And we also know that we have a negative acceleration because the slope of that line is negative. Because both are negative, that means that we are increasing speed. So the way we determine this is if your velocity and acceleration are both the same sign, your speed increases. If your velocity and acceleration are a different sign, then you would decrease. Like right here, we have positive velocity and positive acceleration. So therefore you have increasing speed. Okay. So here we also have increasing speed. So at this point, what we need to do is we need to graph, if we go up like this, okay, we're going to be having a positive displacement, which means a positive velocity. And we don't. We have a negative velocity, which means that the object starts moving backwards. This is a position time graph. So if the object is moving backwards, the graph has to end up some point over here. So I'm just going to say it ends up right here. Okay, just at 7. It's going to end up below from what the forward position is. Now, the question is, okay, what's going to happen? Is it going to be something that looks like this? Okay, or is it going to be something that looks like this? Okay, so that is our question. How do we decide which one it is? Now, if you notice, your acceleration is negative. Therefore, or actually we know it's increasing velocity here. So that means your slope needs to be getting bigger as we go along. This slope right here, at the end right here, it's going to reach 0. Okay, so this one here is getting bigger and bigger. So remember, the slope is a slope of the tangent, or the acceleration is the slope of the tangent line to that graph. Notice how this one here goes from 0, and then it gradually starts getting bigger and bigger, or more sloped. So that means that we're going to choose this top one right here. Okay, so I'm going to erase all my little marks right here, and I'm just going to draw my graph like this. Okay, so again, and this would be your sketch. Now, notice one key difference between, so this is position, this is time. One key difference between this graph and this one right here, okay? Part D said to plot, so that means that you actually have to include the values, okay? You need to make sure you calculate the values. Part E simply said to sketch. When you sketch a graph, you do need to have the overall shape of the graph, but you don't really have to do any actual values like we did over here. Okay, so for part D, it wouldn't have been fine just to put a line right here and then a horizontal line over here without labeling your points. Okay, you actually needed to plot, so you needed to be able to have exactly what your acceleration is. For the position time graph, it simply said sketch, so we really don't know what this position is here. We really the problem is not asking us to find that position. We could if we find the displacement, which we have already done, okay? But it's really not asking us to do that, okay? So we don't have to include anything. We still have to label our time axis. We still need to label our y-axis, and because we know time for sure is going to be between 0 and 7 seconds, we can label that, but we don't need to label the y-axis or the position axis. Okay, and then that's the end. Okay, that's how you solve this FRQ.